Hello everybody, my name is Sophie Comte, I'm Project Manager at the European Cluster of Ceramics, and I begin this webinar with a short introduction about our cluster. Our association has 140 members in 7 countries, and this is COVID-19 time. We have decided to disseminate the know-how of our members, the latest development and products, for example. If it's not done yet, please precise your name and your address email when you log in, so that we can identify you, which allow us to compare with our registration file. Thank you very much for that. Before giving the floor, I would like also to share you the new date of our B2B meeting, Ceramic Network. It will be held in Limoges, the 4 and 5 of November. As I said, this is a B2B meeting about ceramics with also conferences on ceramics and technologies, and also visits of companies. If you are interested or if you don't know yet, I invite you to go on website on this event. You can attend as visitor, it's free, or as exhibitors. Do not hesitate to contact us for more information. We have already proposed you 14 webinars, and it will be the 15th. And here you have a listing of the webinars that will be held next Monday and Tuesday. If a subject grabs your attention, you can go on our website, the event page, and you can register. Today, the webinar is proposed by Lithoz company. It concerns materials and applications for additive manufacturing of ceramics. And Johannes Homa, the CEO of Lithoz, is a speaker. Before he starts his presentation, I would like to give you some recommendation about GoToMeeting buttons. Please switch off the micro and your camera. You have a better display speed, and also it's allowed to avoid disturbing noises. Of course, if you have a question, please use the chat button all along the presentation of Johannes. You can ask your question to the speaker or to the team of the organization, me or Florine Bull, for example, or to everyone, as you want. At the end of the presentation, Florine read it, and Johannes can answer. The presentation of Johannes will be last 40 minutes, and we have 15 minutes for the question. Now I will share the screen of Johannes, and we can start the presentation. Have a good presentation.
So thank you very much for the introduction. Bonjour, Madame et Monsieur. Good afternoon, ladies and gentlemen. It's my pleasure to welcome you on the webinar about additive manufacturing materials and applications. Yeah, as you all know, it's difficult times in these times, and we try to do our best. I have to thank, first of all, Paul Ceramique for giving us the possibility to present here. I'm really happy that so many people have joined this webinar. Actually, there were more participants than we can have at the moment. So as Sophie already said, the webinar will be also available for download afterwards. Okay, I have prepared a small presentation for you about materials, applications, also about a little bit the possibilities we have with additive manufacturing in this crisis, where it can be used, and what we can do. First of all, let me introduce you to Lithoz. We are the leading provider for additive manufacturing solutions. Here you see our team. Last autumn, we are currently more than 70 employees here in Austria and also in the United States. We offer a full 3D printing solution, which means the machines, the printers itself, material, software, customized solution, and also application support. We have currently nearly 80 machines all over the world now, and I think one of the main thing, or one of the best thing to show how good we can partner with our customers is that 25% of our customers have already more than one machine. So we see where people are starting to work with additive manufacturing, they can be successful. Here you see some of our customers throughout the whole world, ranging from KLS Martin, Bosch, Sterix in Germany, to the United States, Aramco, Morgan, but also in Brazil, Plenum, or Australia, Third Axis, Cinema, Alumina. So you name it, we have say more than 40 customers, mainly in the industry, but of course also in the R&D institutes, universities, research organizations. Most well known Fraunhofer, IKTS, for example, having already 3 of our machines, or Alfred University in the US, also well known for ceramics. Yeah, why is additive manufacturing interesting? Why does it make sense to use additive manufacturing? The first thing what you already hear is this freedom of design. So you can make new designs possible with additive manufacturing because the design restrictions are not longer here. Of course, there are design rules. It does not mean that there's a design ignorance, but the design freedom is much, much greater, which gives you then also the opportunity to develop completely new products and trying to get new functions into this product. I will show one of those later, or a couple of those later on. But there's this is really a huge potential for additive manufacturing, but the most difficult one to see, because this is beyond our state of the art. And of course, which is totally clear, is prototyping, to make a couple of prototypes very fast, and to access the mass market with some prototypes, which is especially interested for the powder injection molding industry. And currently we see this in this crisis. When you see here flexibility through digital production, this is now where we can see that additive manufacturing can solve issues in this crisis. Why is it an issue? We have already a couple of companies where the supply chain broke down, so they cannot source their parts anymore. So they need, and since most of these parts are injection molded parts, they need tools, and the tools are now with their supplier, and they are locked down. So so they need a chance to produce somehow these parts. And here, with a digital production technology like additive manufacturing, it's possible to produce these parts without this tool, independent from the location, independent from the company. And I think this fragility of the global supply chain will now come into more and more people's mind, and they will try to use digital production technology much more in the future, maybe as a real production technology, or as a backup technology, where I call it like a digital storage. So they still use mass manufacturing, use conventional forming for mass manufacturing, but, and this is the important thing, they qualify also the additive manufacturing parts for the supply as a demand for later on. So this is something which shows where the crisis can support these issues, and here we will see much more in the next month and years, that companies will go much more into this digital production technologies. And of course, especially if we look into medical devices, mass customization is for sure something which is a very good advantage of additive manufacturing, because once you are in implants, every part is more or less unique, and then every part needs to be different, and this is of course a very big advantage for additive manufacturing. So you see there are a lot of ways how to use additive manufacturing. we've seen in the past that it's sometimes difficult to overcome these first hurdles to get started. But once the companies have started to work with it, a lot of ideas come up, a lot of things happen, and it's going then very, very fast. And yeah, those who are really successful or have been successful in the past, they bought already 2-3 machines because the demand is so high. So basically, it needs time for your customers to understand additive manufacturing. This is a production technology, which means you also need some time to understand additive manufacturing. But once you have overcome these first steps, it's normal to use production technology. When does it make sense to use additive manufacturing? I summarize here a little bit what I've said, but maybe going into more detail on these 3 effects, which I think are important for additive manufacturing. Here, what we see, of course, this is well known. Of course, again, this is just a simplification. So if we have injection molding, the prices go down immediately with the number of parts. And so basically what we see, there's a break-even point, and additive manufacturing is in this simplification always the same price per part. It's of course not totally right, but should be okay for this. But what we see here on the left-hand side, additive manufacturing is more economical, and of course at a certain number of parts, injection molding becomes more economical. So, and this is what we currently see, that people are shifting from injection molding to additive manufacturing if the lot sizes are rather small. So sometimes they have to order for 3, 4, 5 years their parts and cannot change anything. And so they think that they can do something with additive manufacturing. And especially in the medical device industry, this has shown that this works out very well. And we are already, not we, but our customers are already in the production of lot sizes of a couple of thousands up to more than 10,000 parts per year with technology. So you see, additive manufacturing is already in serial production. Another effect, what we see is, I would call it complexity for free effect. Of course, again, a simplification. We see with injection molding, the more complex a part gets, the more complex the tool will be, and hence the prices goes up. For additive manufacturing, complexity is more or less for free. So basically, the complexity has no effect on the price. Again, we see here a break even where there's a certain complexity where it makes sense to really use additive manufacturing also in large quantities. Of course, this is never independent from the lot size, but as a simplification, it shows that there is some area where additive manufacturing is even more economical once the complexity has come up. So this is where I think, this is the easiest thing. These are those things which already are here. But much more interesting is this asymptote on the right-hand side of your screen, because what does it mean? A certain complexity cannot be produced by injection molding or by conventional forming technology, and this is actually the big blue ocean for additive manufacturing. And this is what I think the future of additive manufacturing, although it's hard to think about things which are not existing yet, but we already see these kind of things coming up, and there, you just add some functionality to the parts, and they give you much more value than the costs of the printing. So this is something which will be much more interesting in the future as well. And a very simple thing is size matters in additive manufacturing. And in that case, the smaller the better. Why is it better? Because we are working in parallel, so we can make all parts in parallel, and if you need to make it bigger, if the height is very, very long, it takes just a lot of time. Here you see, for example, two casting cores which have been compared. One is a big one with 27 centimeters in height. It takes 27 hours more or less to print this part. But if we go to the smaller cores, we can print 30 cores in once. They are, of course, also smaller in height, so 73 millimeters, and the build time per part is then 14 minutes. Sorry. So what you see, the smaller the parts, the better it is suited for additive manufacturing, because here we have an effect then which is different to conventional forming technologies. Here, the less material you're using, the better it is for the price. So this was a general introduction into additive manufacturing to give you a little bit of idea of what you can do and where you should use it. And now I want to step in to introduce you to our LCM technology. LCM stands for lithography-based ceramic manufacturing, which means basically that we are using light as a structure. How does it work? Basically, for all those who are ceramics experts, and I think most of you are in this webinar, our technology is a two-step process. So we start with a CAD design, then we print it, and usually then all additive or most of the additive manufacturing technologies are more or less finished. But since we are working with ceramics, we need a post-processing, a thermal post-processing, which means we need to define and sinter the parts to achieve the final product. So this is, again, for me, this is one of the reasons why we can achieve these good mechanical properties, because we have this two-stage approach, which is the normal way of treating ceramic parts. How does the technology basically work? I have here, you can find a lot of explanation videos also on YouTube or on our website, but just very briefly, let me show you how it works. So I think you cannot see my mouse, my pointer, doesn't matter. On the left side, you see an insight into the machine. So we have a ceramic material, a ceramic slurry in a vat, and the parts are drawn out of the vat. So as you can see on the schematic picture on the right hand, there is an optical system underneath the vat. And if you expose from underneath, the light hits the materials. Where the light hits the material, it solidifies, and then you build up the part layer by layer, as with any conventional forming technology. The advantage of this upside down approach is very much that you can make very, very fine details, and you can make also very thin layers. So basically, when you build up from upside down, you have no contact between the blade and the part, and therefore it's unlikely that you destroy the part with the blade, which happens if you expose sometimes from the top. And as well, one of the main issues, and I think this is important also for mass manufacturing, is that the material which you need to provide to build the part is exactly the material which is used by the part. So if you use here the exposure from top, you will need to fill the whole volume of the build chamber to produce a part, and this is sometimes very bad. Additionally, we are using, as you can see here next to number 3, a DMD device. This is a DLP projection system, so which means as well we are exposing one layer at once, so there is no scanning like in the laser technology, and this increases, of course, the productivity of your technology. And additionally, the the quality with the DLP system is comparable or sometimes even better to a laser system, because it depends on many other factors than just the resolution of the DMD or the laser spot. So this was just very briefly how these things work. If you want to have here more information, please check out our website or our YouTube channel. And this is clear. I don't know if you recognize this person in the back, but you see how a CEO shrinks in this process. So, you know, we start with the binder and the ceramic particles, then you burn off the binder, and then the part shrinks and gets the final ceramic properties. But this, as you can see it here, is as with any conventional ceramic forming technology. Here you see our different systems which we provide at the moment. So our first generation was the Serafab 7500. Here we have also a dental model, taking more into account all those issues which comes from medical application. And then the next generation is our Serafab systems, where we have different building envelopes, and it's also a modular design. So you can stake up to 4 machines into one unit to increase your productivity. Because our approach is, and with all the people we talk about in additive manufacturing, from metals and from plastics, they all have the same opinion: to move to take multiple machines rather than one big machine, to keep the flexibility and to really make use of this parallel approach. I don't want to go into details about the differences, what these machines are. You can check it out on the internet, or can contact us if you have any questions. Yeah, here, what about productivity? Is additive manufacturing really capable of serial production? As I already told you, yes, it is. Our customers are already in this serial production. Here I want to show you just a part with dental implants. It's even on the small machine, so to say, on the Serafab 7500 dental. Here you can produce 240 implants per day, which means 60,000 implants per year with a single printer. And if you go now to the next generation printer with the modular setup, you can go to the S65 and, you know, use it 4 times. You can make up to 600,000 implants per year with one single unit. So you see, again, here we see small parts are good for additive manufacturing, and it's possible to really mass produce with these kinds of tools. Yeah, one of the most important things in additive manufacturing are the materials, because, and as I said already, most of you are ceramic experts, so you know that there are 3 main important issues for ceramics. First is quality, second is quality, and third is quality. So it all depends on the quality of the ceramic parts, and therefore it's very important to check it out very well before you make any decision. Basically, our philosophy is that we use the same powders as in conventional forming technology, which means basically we can use all sinterable materials, and we are, this is very important for us in terms of ceramic engineering or ceramic material science, we adapt the technology to the powder and not vice versa. So we take any powder which is provided by the customer or which we buy off the shelf to use in this process. And then the powder can range from couple of other, from 100 nanometers to 100 micrometers. So basically 3 orders of magnitude what we can use in powders, or even more if necessary. We do currently also a lot of customer specific material development. This is where we are very well known for that. Customers providing material and we print the part. And here, just a very important input here, this is already trying to evangelize in those things. So once you have a ceramic part, a 3D printed ceramic part, you have to test it the right way. And this is always, you have to test the weakest link, and this is always the layer boundaries. And we always test our parts like this. And if you make everything perfect, there is no difference in the layer in the direction of testing. But here, as you see it right now, so you're testing along the layer. So you print the part like this, and you test it like this. This is very, very important, because not everybody is following this rule, and sometimes this could lead up to a factor of 10 in strength values. So it's very important to know that, because additive manufacturing is a rather young field, and even some experts, or some, let's say, some already starters with additive manufacturing have difficulties in examining 3D printed parts. And you know, we are trying to be always very honest, very open, and this shows. Again, I mean, if we have 25% of our customers having more than one machine, you can assume that you can then not make any bad mistakes here. Therefore, I think keep this in mind. This is important. All our parts or our material properties are measured like this. Here you see the range, or some of the materials we have already tested. This starts, of course, with alumina, zirconia, also silicone nitride, also materials for resorbable ceramics, tricalcium phosphate, hydroxyapatite, bioglass, but also very special materials like magnesia regolite, which is moon dust, or silica-based materials for casting cores, piezo ceramics, glass ceramics, even the black and white part on the right side. This is a 2K component, so we are working already on 2 component machines and have already them shipped to customers. So we, you know, basically, as I said in the very beginning, we can work on all ceramics basically, and yeah, the range is basically you can use all ceramic parts. Let me go now into some of the details to show you what can we achieve with our standard products. For example, one of our first products was Lithoz HP500, which is an alumina. It has a 4-point bending strength of more than 400 megapascals and density well above 99%. And very special, I think, is also the surface roughness. It's well below 1 micron. The same is true for zirconia. So we have here 3-mole yttrium stabilized zirconia. Also 4-point bending strength, nearly 1000 megapascals. Theoretical density, nearly again 100%. And this shows you that these values are very similar, if not the same, as in conventional forming technology. One of the most difficult materials is silicone nitride, as you already know from conventional ceramic forming technologies. And here, let me show you just a comparison. If we compare LCM to an isopressed part, it's the same powder, the same sintering cycle is used. And basically what you can see here, that there is no difference. It's from the microstructure the same, from the material properties the same. So basically you cannot tell from these pictures whether this has been made by additive manufacturing or not. And one of the main things I would also like to stress is how can you see that you are really doing something good? And here I would propose to look into polycrystalline ceramics. to make them transparent. So basically, we could show here that this is the Champions League of ceramic processing. So here you see a normal alumina powder, which has been manufactured by our LCM technology, has been, of course, hipped, but it can be made very translucent, as you know from other ceramic pouring processes, and here you cannot hide anything. If you can do these translucent things, there can be no flaw in it. So every crack, every air bubble, every problems at the grain boundaries you would see here, and I think this is, I call this always the Champions League of ceramics. So if you can do this, you can show that you are really playing in the world class here. And also you can see here a micrograph from these hipped samples, and the average grain size is well below 1 micron. So finally, let me also come to the industries and application. I promised you to show you some samples of where additive manufacturing in ceramics is already used, and yeah, I want to structure them in terms of industry. Of course, one of the main industries which we are working is the medical industries. As I said, all personal implants, they are unique parts, and therefore additive manufacturing is here really the technology of the choice. And we have already printers in Europe, in North and South America already, as well in Australia. So more or less all over the world, people or companies are making resorbable and non-resorbable implants. Our customers have also already filed CE certification here in Europe for medical device class 3. So this is the highest class, which means they are implanted into the body and are in contact with body fluid. And this has been already issued by Europe, and also the FDA, the Food and Drug Administration in USA, has already approved the class 2 of our products there. Why not class 3 yet? Because nobody has done it yet in the US. But the class 3 is already, 2A is already in place. And if we're talking about class 3, we are really proud to say that already 20 surgeries have been performed since 2017 with our technology, with our materials, with bone replacement materials. So it was a tricalcium phosphate which has been implanted, and I still remember when I was when we knew that the first surgery was taking place. We were really nervous, because once you know that now your parts are really going into humans, this is a very special moment, and I was very happy that everything went fine, and up to our knowledge, all 20 people, all 20 patients are still alive and happily living with our implants. I also told you that we're also doing dental parts. Here, of course, we are in. We can do different things. On the one hand, the crowns and bridges and veneers, as you see here, but also implants, either of zirconia or even silicone nitride is possible. So different things. Basically, what I think here with additive manufacturing is that one should find those applications where additive manufacturing can really give an added value, and this is especially true for this ultra thin veneers. So you can make very, very thin veneers, and with very accurate surface and geometry, especially on the occlusal surface, and this is not possible with milling. But here we have already done some tests and some trials. yeah, here I want to show you one of the examples where you can really make use of additive manufacturing. This has been done by one of our customers, Alumina Systems in Germany. They were developing this kind of ring. It's for an etching and coating process in the semiconductor industry. In the past, it has been made out of titanium, and they had to change it quite often. So first of all, they were making it of alumina, and which of course makes the which withstand this acidic environment, but they also developed a special nozzle design with additive manufacturing, and this is actually how additive manufacturing can be properly used, because they were increasing then, or let's say first of all, they were decreasing the coating time by 2/3. So instead of taking 3 minutes, it took 1 minute. So, and this means that they could increase the productivity by 200%. So basically, when you had to buy in the past 3 machines, you can now buy just 1 machine by using this kind of coating process. And this is one of these examples, which I said in the beginning, where you can really add a lot of value to your customer or to the product, and then it is not so important how much this ring costs, because it saves 2 machines which are worth each over $1 million. So basically, you can imagine that the discussion about the prices of these rings are not the most important one, rather than can it be supplied and does it fulfill our requirements. I think this is one of the very good examples to show how additive manufacturing can be used. One of the one of the other markets which is very, very interesting for additive manufacturing is casting cores for turbine blades. So as you maybe know, turbine blades are already casted, but they want to increase always the temperature in the burning chamber, which means they need to cool the turbine blades even better, because they are already exceeding the temperature of the melting temperature of the metal. So they already have some things in place to cool the blade, and they use, of course, air cooling to cool the blade, and they need then these casting cores. And they already know, or the turbine blade industry already knows, that the new generation of casting cores can be will have a multi-wall design, which means you cannot injection mold them anymore. So it's really a very complex part. And when I look back, maybe 4 or 5 years ago, additive manufacturing was one of the possible solutions for solving this problem. And now my feeling is that it's one of the best candidates to achieve, or one of the best candidates to be used for mass manufacturing these new generations of cores. But of course, we are talking here about innovation cycles of 10 to 15 years. So it takes some time, but we are already qualifying our technology with some turbine manufacturers, and they have already successfully casted single crystal material with our technology. And here we see really one of the strong demands here in this field, as well as in the medical field. So basically, if you want, we have about 40% in the technical ceramic markets, about 30% bioceramics, and 30% in these gas turbines, and these are all growing fields. So sometimes we have to really make sure we can cope with all of this demand. Yeah, let me sum up a little bit my presentation so that we have enough time for questions. I think if you really want to use additive manufacturing, we are committed to your vision of innovation. So we see ourselves as partners, and we want to support you. And as I could show you right now, we have 3D printing can be used for all different kind of ceramics. The biggest challenge is actually to re-educate the engineers to make use of this new design freedom and think in these new ways, to think differently. This is, I think, one of the biggest challenge every engineer has, not only in ceramics, also in metals and plastics. And this is what we currently see in this crisis, that you could increase a lot your competitiveness in the market, because the global supply chain is not as stable as it was supposed to be. And with additive manufacturing, you could on the one hand, have a digital tool-less manufacturing technology, but also a production opportunity for small scale series and small lot sizes, where a tool investment is economically not feasible. And here we will see much more applications after this crisis in additive manufacturing. Yeah, I already was talking about the different industries which we are working in, and yeah, last but not last, still have some slides, but I think to summarize what I've said is, as well, we are talking here about the manufacturing technology. It's not a toy. It's from this point of view very similar to injection molding. You need to build up your know-how, and therefore we have a very big advantage that we can really cover all the process chain in-house. We do not only do machine development, material development, we do also software development, and are also supporting our customers in application development. And in the past, and still, we focus very much on quality and on technological leadership. By doing this, we have achieved to be world market leader and still the leading edge in ceramic additive manufacturing. We do also a lot of innovation, a lot of R&D cooperation, not only in Austria, in Europe, in the US, in China, worldwide. We are really open for any kind of R&D collaborations. And in this sense, we see our customers more as partners, and all those companies coming up with ideas, we see them as partners. And this shows for me that we have gone in the right way, because so far most of the service providers in ceramics are using our technology for the market. And we have, and 25% of our customers have more than 2 machines. Again, I think this is a sign that we are doing the right thing, that we know how to come into serial production. This is sometimes, it's a way. It's not something now I do it. You have to learn it, as you have to do as you have to learn injection molding, and as you have to learn cycling. But I think that we really can show that it's possible, and hopefully we will also have some more stories to share with you. But as you can understand, most of the industrial partner, they don't want to share their really good ongoing projects with the public, which means with their competition. But this is for us very important, to be seen as a partner and to support our customers. Yeah, last but not least, let me end with a question. Why is it important to deal with additive manufacturing? I've still 1 minute and I'm finished. Why is it important to deal with additive manufacturing? yeah, we have seen now a lot of applications, a lot of ideas, a lot of things. Everything looks fine, but why can I not use it directly into my in my business? And I think it's very similar to what we have seen in the past, and what in the past people were thinking about computers. And here we have Ken Olsen, the founder and president of Digital Equipment Corporation, so one of those who were introducing computers. And he said at this time, there is no reason why anyone won't want a computer in their home. Imagine or think how many computers do you have right now? One mobile phone, a computer, in your car, a computer, everywhere. So basically, this is the difficult thing to look from now into the future and try to find applications where additive manufacturing can be used. And they had it 50 years ago. They had the very, very same problems, and now we cannot live without computer. And I think this will be also very true for additive manufacturing, and we already see it here. So I would like to thank you for listening to my presentation. We have still 15 minutes for question and answers. If there are more questions, or if some questions cannot be answered, please feel free to reach out to us. You can access our contact details from the website, or even if you want to contact me directly, feel free to send me an email, feel free to call me, whatever you want in this time. Basically, it's anyway, sometimes times are more silent than it was, and without being able to travel, we have to switch to phones and emails. Yes. But I would be happy to answer all your questions, and I will then if you email me as well. So thank you very much again for listening, and I'm happy now to receive your answers.
Yes, thank you very much. Thank you very much, Johannes. Have you some questions, Florine?
Yes, it's Florine Bull. So thank you, Johannes, for your very nice presentation, very interesting about your technology. We have many questions on the chat, so I will sort them. So the first one concerns the ceramic implants you've shown at the beginning of your presentation. Are they certified for dental application? And if yes, what kind of certification has been performed by your customer?
Yeah. Basically, we cannot certify certain applications ourselves because this is usually what our customers do, because we are not the ones who get the implants into the market. So this is basically something which the customers have to do themselves. But as I already was pointing out, it has been shown that really the highest class of implants, the resorbable implants, can be certified by the legal bodies.
Okay, thank you. Another question concerning a comparison with another technology. Is LCM a better technology than SLA for the same application?
Yeah, basically, to be honest, there is nothing like a superior technology. It depends so much on the application. So basically, for every application, you will have a best matching technology. What I was pointing out, the LCM technology is really used. So the advantage is that it's easy to use because lasers are sometimes very difficult to use. It's very complex to use them. They have shifting, they are drifting, and the hedging. This is complex, and it takes also some time. So therefore, I mean, we have in our labs we have everything in use. So we have exposure from top, exposure from the bottom, exposure with laser, exposure with DLP. And we've tried out all those things, and we strongly think that exposing with DLP and with the SDLCM technology is the best starting point to get things running, and the easiest way to see. And yeah, as I said, this is the technology which is mostly used by service providers.
Okay, we have another question from someone in the field of prosthodontics. I wonder, what is your opinion about manufacturing time of crowns customized for individual patients in comparison with the CNC, as additive manufacturing requires longer binding time, and time is great value in this field?
Yeah, thank you very much for this question. I was already trying to point out this a little bit. Of course, milling is already an established technology, and it's working very, very well. I think that that additive manufacturing should be used where the other technologies are not capable anymore. And to just produce a normal crown by additive manufacturing does not give you really a lot of added value. You can either use it really for mass manufacturing. If you're talking about 1,000 crowns per day or even more, then it makes sense to look into additive manufacturing, because then you can make use of the parallelity of the process. And additionally, what I was trying to show is these ultra thin veneers where the wall thicknesses are very, very thin, 200 microns. They are additive manufacturing really makes sense, and they are much more application in the dental field than just printing normal crowns, which can also be milled.
Okay, thank you. We have another question. Can you comment on the use of DMD-based optical system in your machine instead of LCD-based optical system?
Okay, yeah. Why we don't use LCD? Yeah, this is a matter of light intensity and of quality. So basically, LCDs can be used for plastics, but still most commonly is DMDs which are used, and we don't think that at this level where the LCDs are at the moment, that they can be really used for ceramic additive manufacturing.
Okay, we have another question about debinding. Concerning the debinding step, what is the debinding method you use? How long does it take? And what kind of equipment are necessary?
Yeah, we are using thermal debinding only, which means we are using the same furnaces as in conventional ceramic debinding, so very, very similar to injection molding, but again, just a thermal debinding step, so there is no catalytic and no solvent debinding. And this is, of course, the most time-consuming process, and it depends very much on the geometry and very much on the wall thickness of the parts. It can be done within a day, or sometimes takes even more.
Okay, and then the same person asked another question. It's Elio Jorge from CTCV Portugal. Have you got an LCM model for research laboratories? That means maybe smaller, not too much automated, resulting in a friendly price.
Yeah, maybe we should reach out to Jorge and talk to him. We have some ideas about that. I will get directly in contact with him.
Yes, no problem. Can you print metals with your equipment?
Thank you very much for this question. Yes, we have started to work on metals, and since I was talking in the beginning about the materials, I was saying that basically all sin-travel materials can be processed, and that's true. So we can also process metals, but we had to adapt the technology. So we were developing a very, it's still a very similar technology, but with some of the differences. It's called the LLM technology, so lithography-based metal manufacturing, and we have spun this technology out into a new company, which is called Incus. It's INCUS. Please, either you email me or you you check out the website about printing metals, which is also performing quite well.
And a complementary question from my side: have you ever tried multi-material printing?
Yeah, we already started to print multi-material. As I was showing with the slides with the different parts, we could see a part with 2 different colors, and we are already selling 2K machines. We have not marketed so far because it's more for research organizations at the moment, and we thought it's not yet ready because we have very high standard on what we think should be used for industrial applications. But the machine has been seen by some of the research organizations, and they just bought it right away as it is in this prototyping stage. And you will see much more in the next years on 2 components in additive manufacturing.
Okay, thank you. What about the green density? No problem with the shrinkage, homogeneous one, even for complex shape?
Yeah, very interesting question. Shrinkage is always an issue. Of course, as I was showing in my slides as well, there is shrinkage involved. Yes, that's true, but it's homogeneous. And the problem is that the thing is, if you have a homogeneous green body, the shrinkage is also homogeneous. So basically, what we know from other ceramic forming technologies is that the green density is not homogeneous due to either in injection molding to bind the powder separation due to the high shear forces, or in dry pressing to the gradient, to the pressure gradient. But here we are using just light as a structuring method, and therefore we have not really any forces, and we can build up a very homogeneous body, and therefore we have no problems with shrinkage. It's just a number which you not even have to type it in, but which you just, if you use alumina, for example, it automatically uses the value it needs and prints out the part larger, and then in the furnace it shrinks, and we can reproduce this well below by 10 microns with different machines, with different places on the machine. So this is really very, very reproducible.
And maybe we can take another last question from the same participant. The binding is one of the key parameters because very long. What is the average percentage of organic parts? Are you looking for innovative way to decompose binder parts faster?
Yeah. I mean, this is always an issue. If we find innovative ways to decompose it faster, very welcome. Any suggestion is very welcome. We do working on those things as well, but yeah, we have a very similar issue as in injection molding. So we have binder contents for, let's say, the technical ceramic issue of over 40%, and this is of course tricky to debind, but this is a well-known ceramic manufacturing problem.
Okay, thank you very much, Johannes. I see it's time to close the session.
Yes.
Thank you to all the participants to this session. Sophie, maybe if you want to conclude
Yes, probably you could review this presentation in video on our website in the next day, and we will send you probably also a satisfaction survey the next month. Thank you for your answer, which will allow to provide